Hi, class. Welcome to the next chapter, chapter 11. We are going to start with chapter 11.1, which is modeling with differential equations. So we're going to start off this section by first talking about what a differential equation is, what do the solutions look like to differential equations, and then we'll get into the modeling aspect of modeling with a differential equation. Um, so we'll do a little bit of front loading, really kind of just understanding what these things are, um, and how they work and what they represent. And then we'll get into some of the different common models that we'll run across and how to create a model for a system, for a physical system phenomenon by using differential equations. Okay. I guess I should say before we start this, differential equations is generally its own course. I do have an entire playlist of differential equations for the course that I tend to teach. Um, it's a very, very, very big area of mathematics. There's a lot of research that goes on. It is an applied sort of form of mathematics that applies to engineering and physics. Differential equations come up everywhere when you're studying the physical sciences, right? Chemistry, biology, all of those things. So let's go ahead and get started. Okay, so a differential equation, or a DE for short, which we will use quite often, is an equation that contains derivatives. So generally, we're used to, in algebra, our equations have a bunch of x's everywhere, and we're trying to solve for x or factor or whatever it is that we're trying to do. Maybe we have a rational function, we're trying to graph it, all the things that you're used to. So the difference here is that all of our equations now can have some form of a derivative. Okay, when I say some form, this can mean that we have a standard derivative, we can have a partial derivative, which uh, you don't really get into until calculus 3, um, or we can have high order derivatives in our equation. So first, second, third, fourth, fifth, thousandth order derivatives. Okay. The solution that we need from a differential equation is not a value. We are not looking for x equals 3, x equals pi, x equals 1/2. That's not what we're looking for. We're looking for a function, okay? A solution to a differential equation is a function that satisfies the equation that contains derivatives in it, okay? So this could be a single function or a family of functions. So family of functions generally means that we have infinite solutions, okay? We generally call this solution y, right? Y is generally the function that we talk about, and this has to satisfy a differential equation, okay? We can categorize our differential equations in numerous ways. We'll talk about some classifications, so then we can, depending on what kind of differential equation we have, depends on determines the method or the approach that we take to a differential to solving a DE. So it's very important to be able to categorize these things, right? Just like in algebra, I know what a polynomial looks like. I know what a rational function looks like. I know what a trig function looks like, right? So the different functions we play with, we're able to categorize. So I want to be able to do that for these equations that I'm trying to solve as well. So one of the first things that we study is ordinary differential equations, okay, or what we call ODEs, and that's what we'll talk about in this chapter, okay. The other kind, right, the big split is between ODEs and PDEs. A PDE is a partial differential equation. It contains partial derivatives, which again, uh, you don't talk about until calculus 3, okay, so PDE. So we will not be talking about those at all in this course. Another way of categorizing a differential equation is by its order, right? It would be, think about the way you categorize a polynomial. You look at its degree, right? The highest degree. This is a fifth degree polynomial. This is a fourth degree polynomial. We classify uh, ODEs, differential equations, in the same manner. We look at the order. Okay, the order is the highest derivative present uh, in the equation. Okay, so let's look at an example. A first order equation will have its highest order, right? Its highest derivative that shows up is just the first derivative. So something like the first derivative of the function y plus that function y equals 2x. Okay, So in order to solve that, I would need a function that when I differentiate it and then add it to itself, I get out 2x. Okay. A second order dE would be something like this. The highest derivative that shows up is the second derivative. So this is the second order differential equation. So here, um, for our example, right, y double prime minus y prime plus 3y equals 2x. So the second derivative minus the first derivative plus 3 times my function will equal 2x. So I would need to find a function that satisfies this um, combination of derivatives, right? Third order equation obviously should have at most a third order derivative in it, right? Y triple prime minus y prime plus 3y. You see, I did not include a double prime term, which is fine. You know, it's very possible that there's not one in there. In fact, it could just be that the third derivative of something equals 2x, right? So I'm just giving examples of equations here, okay, of differential equations, and so forth and so forth and so forth, right? So the highest order derivative that shows up is the order of the differential equation. We also classify differential equations by their linearity, okay? So again, that falls into two categories. It's either linear or it's not linear, okay? So what does it mean by linear? A linear means that the functions of y that appear are at most a degree of one. Again, degree, not order, okay? So these are linear, right? Because the highest degree of y that shows up is just y to the first power, right? So an example of a nonlinear dE would be something like this. Now you might be saying on first glance, well, look, it's just a y, right? There's only a y, even though it's y times y prime. But if we were to change this into what's called the standard order, which is to look more like a polynomial in form, right? So that I would have the highest degree of the dE kind of isolated. It could have a scalar multiple there, a coefficient, but maybe not a function. So let's say I divided everything by y. This would be y prime minus 3x equals x over y. So then the term that would be there would not be a degree of 1, it would be a degree of -1, right? So the problem that I have here is this y times its own derivative, right? So the y times y prime is our non-linear term, okay? Here, the problem is this y squared term because it is not a degree of 1. Here, it's just a second derivative. I'm writing it in a slightly different form, right? I'm using that Leibniz notation. So you have to be able to change your brain and, you know, pattern recognize that sometimes we write as prime, sometimes we write it with the dx dy's, right? The Leibniz notation. And then there's other variations of this as well. So make sure you're familiar with how to represent a derivative, okay? So again, here, this y squared is the nonlinear term because it is not a degree of 1. So here in these examples, these three, these are all linear, okay? These are two examples of non-linear d's. Okay, we also classify these according to their homogeneity, okay? Homogeneity means, is it homogeneous or is it non-homogeneous? Okay, homogeneous means, is it equal to 0 or not equal to 0? Okay. So if a dE is equal to 0, when I have it in its standard form, again, this is standard form, highest derivative, and then in decreasing order of derivatives, really very much so like a polynomial, okay? All of the y's on one side as much as possible, and all of the non-y terms on the other side. So as you can see here, this is a 2x. It is not equal to 0. This is non-homogeneous, right? It is not equal to 0. So homogeneity means that when it's in standard form, 0 is on one side of the equal sign, okay? So standard form, again, y and all of its derivatives on one side of the equation, okay? If it's equal to 0, it's homogeneous. If it's not, it's non-homogeneous. So an example, the second derivative of y minus y squared equals 0. That is a homogeneous equation. All of the y's are on one side. Now this is not linear, okay, but it is homogeneous. Here, all the y's are on one side. All the stuff that's not y is on the other side. This is non-homogeneous because I am not equal to 0 once I put it into standard form. Both of these are second order equations. Okay, it's actually the exact same equation, just one is homogeneous and the other is not. Okay, the last sort of classification that we have is based on its conditions. So remember, our solutions are functions. I can put a condition on a function, right? What does a condition mean? This means that, let's say, when I plug in 1 into my function, I get out 1,000. That's a condition, right? So I can place conditions on my solutions, and the different kind of conditions that I place on my solutions that I need um, determine the type of problem as well, right? So one of those are initial conditions. If I have an initial condition, then what I have is called an initial value problem or an IVP, okay? An initial condition is when y equals 0 or x equals 0. So what happens to my function at the start? When x is 0, what's happening? That's going to be an initial condition. If I have an initial condition, then my differential equation is an initial value problem. Okay. The second is a boundary value problem. So a boundary means I'm looking at what happens at a boundary. Okay. We call these BVPs, boundary value problems. So maybe I'm looking at the different, let's just kind of throw out a huge example right now. Let's say that I have a rod, a metal rod, and I'm heating up the rod with a blowtorch at one end. I can have a differential equation that models the flow of heat through that rod. Okay. Now, I know the temperature of my flame. Okay. And so at one end of the rod has to have a temperature equal to the temperature of my flame. It can't be higher than that, and it shouldn't be lower than that. And so that would be a value for the initial heat on one end. And maybe I need to heat up my rod until at the other end, right, the terminal side, that it is at a different temperature. I need at this end that it's, 500 degrees or what have you. That would be a condition on the boundary, right? So that would be an example of a boundary value problem because I have conditions on both ends, right? An IVP, initial value problem, is a differential equation that has conditions placed on the initial value of any of the solutions that I have that might work for my differential equation. A boundary value problem is a differential equation that has conditions placed on the end boundary of a potential solution, right? If I have conditions on both the beginning and the end, then it is a boundary value problem. So the boundary value problem supersedes an initial value problem. So if I have any sort of boundary condition, even if I have initial conditions or no initial conditions, it's a boundary value problem. Okay, so once there's a condition on a boundary, on an end boundary, it's a boundary value problem. We're not going to get too much into those. We will talk about really mostly about initial values because that's what's most important, but we will also, a little bit talk about boundary values as well. So let's do an example. Okay, so let's say that my differential equation is the second derivative of y minus the first derivative plus 3 times the function y is equal to 2x, right? So you've seen this before. So if I want to classify this, it's very clear that this is a second order equation. It's linear because the highest power of y is the first power. And it is non-homogeneous because in standard form, I'm equal to some function. I'm not equal to 0. I have some function. The function is 2 of x here. So this would be a linear second order non-homogeneous equation. If I'm looking at what happens at 0, then this turns into an initial value problem because I'm saying at the start of my function, when I plug in 0, I should get out 1. At the second derivative, if I plug in 0, I should get out -1. Okay, so this is an initial value problem because I'm talking about what happens at the start of my solution, right? So for my solution, if I plug in 0, I should get 1. If I take the derivative of my solution and I plug in 0, I should get out -1. Okay, I have the same function. Here, this is not at 0, So this is at a boundary. Okay, this is a boundary condition. And so at that same boundary of x equals 1, my derivative should have an output value of -1. So this is a boundary value problem. Okay. Here, this is a first order linear. Okay. Highest degree is 1, non-homogeneous. Okay. I have an initial condition, and then at pi, right, especially since I have a cosine function here, at pi, I get out 1. This is a boundary condition. Okay. So since I have an initial condition and a boundary condition, it's a boundary value problem. Right? And so here I was already kind of putting all of those classifications together. And so we'll go through a couple more examples here where that's our intent, right? To classify these. So this problem, maybe pause, take a guess for yourself, right? Pause the video and say, let me classify this. So what is the order? Is it linear or nonlinear? Is it homogeneous or non-homogeneous, right? So it's second order. Highest degree is more than 1 for y, so this is nonlinear, and it is not equal to 0 in standard form, so this is non-homogeneous, right? So this is a second order, non-homogeneous, non-linear ODE. Okay. Here, x cubed, y triple prime, minus 8y prime equals 0, so same thing. Pause it, look at the order, look at the homogeneity, look at the linearity, and see if you can figure it out. And so hopefully you did that, and we're back now. The highest degree of y there is none, okay? So it's linear. The highest order is 3, third derivative, so it's a third order, and it's equal to 0. This x cubed here has nothing to do with what's going on in my classification, right? Because it's all about what's happening with y. And so this is a third order homogeneous linear ODE. Okay, third order linear homogeneous ODE. This, you've probably never even seen this notation in your life. And that's because has partial derivatives. Okay, again, you see this in Calc 3. I just kind of want to expose you to this, that things get a lot weirder than they are already. And so my function of uh, interest here is u, and it's got x's, y's, and z's, okay, and t's. So this has multivariable, it's a multivariable function, um, which means that we are living in higher level dimensions, right? This would be a third dimension problem with time included. And so this is linear, second order, because we have second partial derivatives. Again, you wouldn't know that, but that's fine. And it is homogeneous because it is only functions of u showing up everywhere. This is a PDE. I am not going to ask you to classify anything for PDEs. I just wanted to expose you and give you an example. Okay. So if we come back here, I should put an extra pause here. But this is our function. I have x cubed y prime minus 8y equals sine of x, and y of 0 equals 0. So this is an initial condition because the condition on the solution is at 0. It's non-homogeneous because it's equal to some function. Highest order is 1. For my y's, the highest power I see is 1. So this is a first order linear non-homogeneous initial value problem. First order linear non-homogeneous IVP. So for the next section, I titled this solutions look different, and that's because again, my solutions are functions. I am not looking for x equals 7, right? I'm not looking for a value. I am looking for a function, and it could be a very long function. Once you get into this course, differential equations, the it's a hard course, is all I'm gonna say. Okay, so there's a lot of calculus. Do not forget your calculus before you go into differential equations. My advice to you is before you take DEs, if you remember me saying this to you, you know, and a couple semesters from now when you do decide to take it, definitely review your calculus before you take differential equations. It is nothing but calculus. It's nothing but integrals, nothing but derivatives. It's a lot of third dimension stuff, a lot of calculus 3. Okay, so make sure you brush up on that stuff. Best advice I can give you. The solution to a differential equation, again, is a function or a family of functions. Okay, the way that I determine whether it's a single function or a family of functions, we're not really going to get into now, but it really depends on if I have an IVP or a DVP, or I'm sorry, a BVP. If I have an IVP and I have enough initial conditions, I can narrow down my family of functions. Okay, so again, to reiterate, I am not looking for a number. I'm looking for a function, right? In order to verify that a function is an actual solution, just like in regular algebra, when I solve for x equals something and I plug it back into my equation, I do the exact same thing. If I have a function that I think is a solution, I plug it right back into my equation and I work out the problem, and everything should balance out with the equal sign. So the way I verify is just like in algebra. However, my solutions are now a function instead of x, okay, a value. So initial conditions, I see, allow us to narrow down a specific solution, a specific function out of a family of functions, okay? We cannot do the same thing if it's boundary conditions, BCs. So if I have some boundary conditions, I may not necessarily be able to take this family of solutions, of possible solutions, and narrow it down to a single solution, okay? Which is fine. Sometimes we want the family of solutions and we don't need an exact solution, right? Which we will see. So let's do an example. So consider the function y equals e to the 3x times cosine of 2x, and the equation y double prime minus 6y prime plus 13y equals 0. Okay, so in order to verify if this function y is a solution or not, I'm going to need the second derivative. Okay, so before I can verify that this is a solution or not to this dE, I need to find the appropriate derivative so that I can start to plug things back in. So I'm going to take y equals e to the 3x cosine of 2x, and I'm going to differentiate it twice. Okay, so the first derivative here, this is two different functions. So if you're fuzzy on differentiating, uh, well, we're going to go over a lot of derivatives for this chapter because it is differential equations. If you need a refresher, I suggest that you go to my website, look at the Calc 1 material. At the end of chapter 4, I have a list of derivatives. Okay, so it's all the derivatives. If you took in my class already, then you already know that. If you haven't, and you're just coming in now to this Calc 2, I will post that into Canvas for you guys. If you're looking at this from somewhere else and you didn't go through the whole series, please visit the website and you can go to the Calc 1 stuff, and I have a list of derivatives if you need it. Maybe you don't need it and you remember all your Calc 1 stuff and you don't need to have a refresher. Anyways, this is two functions. When I have two functions, I do the product rule, which is differentiate the first function. So we have 3e to the 3x, and then you multiply that times the second function, leaving it alone. You add to that your first function being normal, and then you differentiate the second function. So this is going to turn into, so cosine changes sign, so this should be a negative sine times of 2x times 2 because of the chain rule, right? So we got that negative 2 from cosine turning into negative sine, okay? So sine of 2x, and then chain rule says that you differentiate the inside, so the derivative of 2x is 2. Combine that with a negative here, right? So I think from here, I just go ahead and differentiate again, but you can, obviously turn this into a negative 2 here. There's really nothing to combine. I could pull out this e to the 3x if I wanted to. It's not really going to help me. So let's just go ahead and find the second derivative. So we'll do the product rule twice. Okay, I think I go a little bit out of order though. So let's go ahead and do the first one. I'm going to go 3e to the 3x, the first derivative, brings this 3 down. Cosine of 2x stays the same. Okay. For the next one, I'm actually differentiating the first term here. So I kind of did it out of order for some reason. It confused me myself when I went through it. I don't know why I did that. Anyways, I'm going to differentiate this first term. So this e to the 3x turns into 3e to the 3x. And then I'm just going to have the sign of 2x here. Okay. So for both functions, all I really did was differentiate the first function and left the second function alone. So for the rest of this, what I'll do is I'm going to differentiate the second function and leave the first function alone. So I just kind of did the same thing to each function, and then I'm going back and doing the second part. So for the next part, I'm going to have 3e to the 3x, and then I'm going to differentiate cosine of 2x. So this will give me a negative sine 2x times 2. Okay, so I just go ahead and throw the negative 2 in front. This is the 3e, the 3x that's still there. And so then I'll have a sine of 2x. Okay, so that's from this part. And, oh no, actually I did do it regular. I just end up getting the same thing. Okay, it doesn't really matter. Here, doing the second part of this, I'm going to get the negative 2 and the cosine. Okay, negative 2 times 2, e to the 3x, and cosine of 2x. Right. So from here, I would like to simplify everything and put it all together. Okay. Actually, I did do product rule here for the whole first one, and then this whole thing is just a product rule here. It just ends up working out that way. It's pretty interesting. Okay, anyways, let's combine our like terms. So all the cosine 2x's, okay, we should be able to add together because there's an e to the 3x in front of all of these, right? So there's no differentiating powers or anything like that. So all of the cosines we can add together and all the sines we can add together. So for cosines, I have 9 of these things, and I have -4, so that'll give me 5. Okay. Here I got a -6 and a -6 of the sines, so altogether that's -12. So now I have my first derivative, I have my second derivative, I have my original function, and I need to plug all of that into my DE and make sure everything cancels out. Okay. So we'll start with the first function, right? The second derivative. Okay. I will subtract from that 6 times the first derivative, and I'll add to that 13 times my function, right? Which is just e to the 3x cosine 2x. So from here, I want to, I, I'm just saying this to my classes. I hate when you do this and you know it's supposed to go to 0, and then you just write equals 0. You got to actually put some work together for me, please. So if I combine my cosines, let's see what happens, right? I have e to the 3x everywhere. So I'm just going to pull out this e to the 3x. If I'm looking at my cosines, the first thing I have is 5 of them. I have -18 of them here, okay? And I have 13 of them here, okay? And that's for my cosines. For my sines, I have -12. I have -2, okay? Oh, I'm sorry, times 6, so +12. And that's it. So that's for my sines. So now I can say, oh, there's 0, right? 5 minus 18 is -13 plus 13 is 0. -12 and 12 is 0. Now it's, give me one step first. Don't just tell me it's equal to 0 because you know it's supposed to be equal to 0. Right? I want to see you guys actually combining stuff. Um, so there we go. Okay. My solution, this is the solution to this DE. When I took its second derivative and its first derivative and I combined them in this manner, it equaled out 0. So that is the solution. Okay. This is a particular solution. Okay. If I were to do the same thing with y equals c1 e to the 3x plus 1 of 2x, I would still come up with a solution. Now, this is what we mean when we talk about a family of solutions. Any scalar multiple of this function is going to satisfy this DE, which means there's an infinite number of solutions, right? If I take this function itself as being multiplied by 1, it'll work. If I take this function and I multiply the whole thing times 12, and then I do its second derivative and first derivative and combine it this way, I will still get out 0. If I take this whole equation and I multiply it times pi, the same thing. If I take this whole equation here and I multiply it times e, okay, that should work also because e is just a constant, right? It's not e to the x, it's just an e. Um, any other constant multiple of this function is going to work, right? Here, C1 is a constant. C1 is some value in R. We would get the same result, okay? So go ahead and verify that for yourself, okay? I may or may not have put that as a classwork problem for students in my class, but in order to verify this for yourself, you would just keep the C1 here, right? So when I do this first derivative, I'm just keeping C1 everywhere it would go. So there should be a C1 in front here and a C1 in front here, because that constant multiple would come out um, in the product rule, right? The difference again is that y equals C1 e to the 3x cosine of 2x represents a family of solutions, which is infinite solutions, because there's infinite scalars, right? There's infinite constants. So the difference between each of these solutions is just the amplitude, right? If I take this and I multiply it times 100, all of my values are 100 times more. I've changed the amplitude, right? But it's still the same function, okay? And all of those would satisfy our differential equation, right? Whereas this is a single solution, right? It is a particular solution um, because it's a specific example, right? So in fact, y equals e to the 3x cosine of 2x represents the solution to this dE that has the initial conditions that if I plug in 0 to the original function, I get out 1. And if I plug in 0 to the derivative, I get out 3, right? So if I plug in 0 to here, this goes to 1, and then I get cosine of 0. Cosine of 0 is 1, right? So it satisfies this initial condition. And if I look at the first derivative here, if I plug in 0, I should get out 3. And so I know that this turns into 1, which is times 3. And when I plug in 0 to sine, I get out 0. So this whole thing goes away. And so, yeah, that satisfies it. If I plug in 0 to the first derivative, I get out 3. So this is a particular solution because the initial conditions were allowed me to kind of narrow down to a specific solution that has these conditions on it. Okay? So again, you can verify this for yourself. Okay? It's good practice for those of you who are watching at home, not in my class, right? So the interval of existence of a solution is the same as the domain over which the solution satisfies the conditions of the DE. Now you might be saying, what the hell are you talking about, Professor Williams? So let's think about this, okay? I have a family of solutions. If I can narrow it down to a single solution, then the domain is the domain for that single solution, okay? So the conditions determine which solution my graph gives, okay? We'll see more of this in 11.2. You'll see this because we'll have actual graphs that make more sense. But we'll go ahead and we'll look at an example right now to help you kind of clarify this, right? So let's say that we have some differential equation. It doesn't really matter what it is, but let's say that it has a solution of y equals 1 over x. Okay, y over x, if you look at the graph of it, it's discontinuous at x equals 0, right? Which makes sense because you plug in 0 here, you're undefined, okay? If we have a condition, right, a boundary condition, in this case, if I were to plug in 1, I should get out 1. That narrows down my solution, okay? Because the real solution here can be any multiple of 1 over x. So, well, in this case, let's say it is just 1 over x. So if this is my condition, this is the graph of 1 over x, okay? If I plug in 1 and get out 1, well, this side, right, the positive side of the discontinuity is where my solution lies. So this is my solution and not this. Because based on my condition that I have, this boundary condition, it takes out the entire possibility that this can work as a solution, this half of it, because I have a discontinuity, right? So here, the domain for my solution would be from 0 to infinity, 0 not included. I can't even consider the stuff on the negative side because this condition is saying it has to be this part. Okay. So the solution here is the positive portion of the function only, and my interval of existence is from 0 to infinity, 0 not included. So if I have conditions, it allows me to narrow down exactly what I need as a solution. Okay. Systems of equations. So just like in algebra, where I can have a system of linear equations, right? And can turn those into matrices and all this fun stuff. Um, in differential equations, it's very common that we have a system of differential equations, right? They can be classified in the exact same way that a single differential equation can be classified. It can be linear or nonlinear, homogeneous, non-homogeneous. It can be, and we can describe the order, okay? So the solution to a system of these is going to be a system of equations. Okay. So example, verify that x1 of t, my first solution, which is 1 over root 3 sine of 2 root 3, and x2, the second solution, the negative form is just opposite in value to x1, so negative 1 over root 3 sine 2 root 3 are both solutions, so a system of equations, right, as a solution, are the solutions for the IVP system of differential equations given by second derivative of the first function is negative 2 times the x1 function. So again, these are functions, not the variable, right? These functions that are given to me. So negative 2 x1 of x, of t, I'm sorry, plus x2 of t, and the second differential equation in that system is that the second derivative of xt is x1 minus 2x2. So this is a second order system, okay, because the highest derivative that's showing up is the second order. It's linear because once we get here, I don't have any powers of these functions that are larger than 1, right? This is just a function, just a function, just our function, and just our second function, okay? It is not in standard order, but if it was in standard order, standard form, where meaning I move this stuff all to one side, it would be equal to 0. Okay, so this is homogeneous as well. Now I have the conditions that when I plug in 0 for x1, I should get out 0. When I plug in 0 to the first derivative of x1, I should get out 1. When I plug in 0 to x2, I should get out 0. And when I plug in 0 to the first derivative of x2, I should get out negative 1. So these are all things that are happening at 0. So this is an IVP, right, as stated above. So this is a second order, linear, homogeneous IVP. Okay, that's how I would classify this. I need a second derivative of both of these functions, right? Nice thing is I don't need to use the first derivative, but I have to use find the first derivative if I need to find the second derivative. So no matter what, I got to differentiate both of these twice. But the nice thing is they are identical. They're just different sign, right? So I need the first and second derivative of both of these functions that have been given to me as possible solutions, right? The first derivative here is cosine of t root 3, and that is because sine changes to cosine, and the derivative of t root 3 is just root 3, so when I multiply that times the constant that's here, it cancels out. Okay, so that's nice. The second derivative is just the derivative of this, so cosine changes to sine, and it changes sine as well, and then chain rule says that I multiply by the derivative of this. So the second derivative of x1 is negative root 3 sine of t root 3. Similarly, for x2 prime, it's the exact same thing, but different sign, which means that this is identical as well, but different signs. Okay, so positive and negatives. Now that I have my first and second derivatives for both x1 and x2, I can plug them into my differential equation. Okay, so let's start with the first one. First derivative of x1 is the same as negative 2x1 plus x2. So we will go ahead and plug that in. So I'm not going to plug in the second derivative of 1 over here. I'm going to work with this, the right-hand side, and I should be able to uh, do my math and combine stuff and all that kind of good things, good stuff, and come out with this first derivative. So what I'm going to do is I'm going to say negative 2 times the x1 function plus x2. I'm going to do the math on it, combine my terms, and it should come out to what I found for the second derivative. Okay, that's how we're going to work this. So I take negative 2, I plug in x1, so you see here 1 over root 3 sine of 2 root 3 plus x2, so I'm just going to take x2 and plug this in. Negative 1 over root 3 sine t of root 3. Okay, so from here, I would like to combine my like terms. I have negative 2 of these. I have negative 1 over here, so altogether there's negative 3 of them. Okay, negative 3 over root 3 sine of 2 root 3. And now you might be saying, well, Professor Williams, that is not the same as what we got here for x1 double prime. There's nothing left for me to do, and it's not the same. But there is. Rationalize your denominator, right? So multiply top and bottom by root 3. Okay, the 3's cancel, and we have x1 double prime. So make sure you are doing everything you need to in order to try to get back to what you have. So pull out all your tricks if you need to. Most of the time, it's very straightforward. Okay, but if you have a rational in the denominator, don't forget to rationalize your denominators. Okay, so we'll do the same thing for x2. X2 double prime. So again, right, x1 double prime is the same as x1 double prime. X2 double prime is just x1 minus 2x2. Let's make that substitution. So I can have my x1 minus 2 of these. And so same thing is kind of happening here. I have negative 2 and a negative. So this is actually positive 2 of these ones, and I have a positive 1 here. So when I add those together, I get a positive 3 over root 3. Rationalize the denominator, and I get root 3 sine of 2 pi 3, which again become the x2 double prime. It's the same thing. Okay. So I verified that those work, but I also need to verify the initial conditions. Yes, it satisfies my equation, my system that I have here, but does it satisfy my initial conditions? So let's check those. Okay. So now that we verify the functions, we have to verify the ICs as well. So when I plug in 0 to the first function, do I get out 0? This is not a statement. This is what I need to verify. So root 3 sine of 0 is in fact 0. So that works. Okay. It says when I plug in 0 to the first derivative of my function, I get out 1. And so if you remember, right, hopefully you have this paper in front of you already, but the first derivatives were cosine and negative cosine t root 3. Okay, just so that we're clear. So when I plug in 0 here, I get cosine of 0, which is in fact 1. Okay. When I plug in 0 here, okay, I get out 0. This should be a negative, actually. That should be a negative. So I will fix that. It's small enough that I don't really care for the lecture, but that should be 0. I'll fix that for the course readers. So if you download the reader, or it'll have the right value in it. Okay. Regardless, it's 0, right? Whether this is positive or negative, I still get 0 out. Okay. And when I plug in 0 to the first derivative, right, I get negative cosine of 0, which is in fact negative 1. So everything works out. Okay. My x1 that I have and the x2 that were given to me, they satisfy the system and they satisfy the initial conditions. It has to satisfy both of those things. Okay. So now we're at the last part. We're going to talk about modeling with DEs, and then we'll actually develop a model 2 at the end here. But what we're going to do is rather quickly, I'm just going to run through some popular models that you might run across, which will be helpful, for your homework and your assignments and stuff like that. but I'm not going to get super deep into it. It'll just kind of give you a nice brief overview of how these things work and what they actually model. So remember what a derivative is. Derivative is an instantaneous rate of change, right? What is the rate of change right now in this instant? Not over a period of time, right? Not over a length. What's the instantaneous change in my position, right? My speed, my velocity, whatever it is that I'm going to use in a model. So whenever I have something that changes, I have a differential equation, okay? And now if you think about the things that change, it's everything. You're literally changing right now, right? I don't even know you, and I know that you're changing. You are getting older every single second, right? You are aging every single second. The things that are going in your body are changing every single second. As you're sitting here listening to me, your weight is fluctuating up and down. Why? Because you're breathing. When you breathe in, you get a little bit heavier, just a little bit. When you breathe out, you get a little bit lighter, right? So your weight is literally fluctuating and changing instantaneously throughout this entire time, okay? Um, what else changes? Traffic, right? Traffic is the flow. There's always a change in traffic. Anything that flows can be modeled with the differential equation as well. So then you have obviously like rocket science, airflow, anything with air resistance, um, the economy, population size. The differential equations are used to model literally anything you can think of that changes over time is modeled with a differential equation. Okay, so we're just gonna again just do a really brief overview of some examples. This is definitely not an exhaustive list. I don't think you can make an exhaustive list. Um, Differential equations are extremely important and is a major area of research. Okay, so let's go ahead and get into it because I know I tend to talk a lot. So let's talk about some models with DE. So we'll talk about the modeling process a little bit and we'll get into some actual models. So a brief overview of the method of trying to model differential equation. It's similar to modeling with um, algebra with a function, although now we're talking about how a function is changing, not just using a function to say, oh, this parabola models how a ball, the projectile motion of a ball. Okay, so when we start using derivatives, we're going to talk about how the ball is changing in position, changing in height, changing in velocity, all of these kinds of things. So it's not going to model the position, but the changes that are going on with the ball as it is being thrown through the air or the projectile. Okay, so recall that the derivatives are used to model rates of change. So things like velocity, acceleration. We use differential equation, or we use derivatives to model related rates, and we use it for optimization, right? Things like finding maxima and minima and concavity, things like that. Okay. We also use derivatives for linear approximation. So this is really just a review of like the application process of Calc 1 for derivatives, right? If I want to make a model out of derivatives or make the differential equation, um, we need to determine what variables are present in our system. Okay, so what changes as our process goes, right? As time goes generally. So we don't always want to put all of the variables that we can think of because then our model can be too convoluted. We really want to try to keep it as simple as possible first, and then as we work on it and find solutions or what have you, we can start to introduce more and more variables and make it more and more convoluted. Okay, um, so we want to keep it very generalized so that we can find something that approximates an answer at least, and then we can get more accurate later by adding more variables. Okay, so this is called specifying the level of resolution. It's very easy to go overboard and just try to create this model that represents everything about a system. It would be very difficult to do, but it'll be even more difficult to try to solve. Okay, so we want to keep things very general. So next, we try to make a set of reasonable assumptions about our system, like um, the initial value will be this, right? The end value will be that. right? So setting some conditions on the model. Um, Maybe we end up creating more than one equation, right? And we want to say, oh, these equations relate to each other in this manner. And so then we create a system of equations, okay? So the assumptions are going to include any calculations that are derived from the formulas that we use in order to create the system, right? And so let's go ahead and just kind of go through this process for a couple of examples. So I took this from my differential equations course. I left out a bunch of examples as well because we just won't end up going over them. But these are things that you're pretty likely to see in a calculus course or a physics course, right? So first thing, 100% is population growth. Every calculus 2 textbook tends to use population growth as um, their their example, right? They always want to talk about population growth because we've dealt with population growth a lot, right? When you talk about continuous growth, um, we generally use that in the sense of money, but it works for population as well, okay? So for population growth, the rate of change of my population over time is some constant multiple of the population. And so I'm not going to get too deep into it, but for this very example, I will. Think about this. If my population is small, it's going to have a very large rate of growth. Okay. Um, let's say that I have a population of animals and there's only two of them. If those two things breed and they have, let's say, 4 children, my population just went from 2 to 6. It just tripled in size. Now, let's say that I have a population of 1,000 of something, it's going to grow even slower because there's already a lot of things. They're not all having babies at the same time. They have children at different rates, right? At different intervals. And so the growth is smaller because maybe out of those 1,000 people, there's only 50 of them are having kids together, right? And so the rate of growth is a lot smaller compared to the total size of the population at that time. So generally, when I have a large population, the rate of growth is a little bit slower than for a smaller population. But that, as an example, the rate of growth of a population instantaneously at any time is a constant multiple of that population size. Okay, so P of T, this large P, is the population at time T. Um, K is larger than 0. Okay, that doesn't necessarily mean it has to be larger than 1. Right? If this was like zero point 0.8, for instance, my population would be shrinking at that point. Okay, I'm sorry. Yeah, it'll be shrinking because it's less than 1. Growth would be larger than 1. Okay, and so I'm larger than 0, and that's my constant of proportionality. Okay. Next is radioactive decay, which is actually very, very, very similar to population growth. Okay. The rate of change of an amount of a substance at time t is a constant multiple of the amount of substance. If I have a lot of a substance, then it's gonna grow or it's gonna decay fast, right? If I have a little bit, it'll decay faster because there's less of it. Um, and so the new amount would be a lot less proportionally, right, than if there's a lot of it. T is the amount of a substance at times t. K here is less than 0, so it's a negative growth model. Okay. So again, very similar here. This is positive because it's growth. This is decay, so it's negative. I know I did say it was zero point 0.8 would have been a decay, but zero point 0.8 was still a growth. Actually, it's just that the rate of growth is slower than if it was larger than 1. Newton's law of cooling, very, very similar. The temperature at time t is a constant multiple in the difference in temperature of an object and its surrounding medium. Okay, so for instance, um, my rate of change is going to be larger if this is a large difference, right? So let's say I put something cold, okay? Let's say my temperature is very cold in an oven, okay? I'm going to bake a frozen pie or something. There's a huge difference in the temperature between those. So the change in temperature is going to be very large, right? You can also think about this if I have a very hot coffee and it's cold outside. I have a very large difference between the temperatures, right? 'Cause this is cooling, not heating. And so it's a constant multiple in the difference in the temperatures, okay? If I have a hot coffee or tea and it's hot outside, then the difference between the temperatures is a lot smaller. And so it's going to cool off a lot slower once the temperatures get close to each other, okay? T of T is the temperature of an object at time T. T of M is the temperature of the surrounding medium. So this could be outside, indoors, in an oven, um, what have you, right? In your car, doesn't really matter. If the ambient temperature, the surrounding temperature, is a real number, then K is less than 0 because this is cooling, right? We are cooling down. T is approaching T of M. Spread of disease, okay? If X is the population, right? The population of time T that is infected with a disease is a constant multiple of the number of interactions of that population X with a diseased population Y. Okay, X of T is the amount of diseased people at time T. Y of T is the amount of people that is not diseased at time T. And XY represents the number of interactions between the two groups. Okay, here, this is spread of disease. If K is positive, then it's a positive spread. If K is negative, then it's a decreasing number spread. Okay, chemical reactions. So a first order reaction is when we have a substance that is undergoing a chemical reaction, and so it is decaying, it's decomposing, okay? And that is modeled by the amount of a substance at time t is a constant multiple of that amount of substance present. I don't know if you've noticed, but it's most of these differential equations are very similar in form, okay? X of t is the amount of a substance remaining at time t as it decomposes to smaller molecules. Okay, so this is a decomposition reaction, right? Here K is negative, right? Because I'm decomposing into its composition elements, and so the amount of my um, substance is decaying, right? So this is negative. A second order reaction is when you have two elements that are interacting with each other, right? So this is a chemical reaction where, um, right, you could think of it like a piece of metal resting, right? It's the metal plus oxygen are interacting together to create rest, right? So a substance A and B are combining to create a new substance C, okay? And this is modeled by the amount of substance of x at time t is a constant multiple of the number of interactions between A and B that are left. Okay, so x of t is the amount of substance C. So this x here, so this is the amount of the substance that is created at t during the chemical reaction. Alpha minus x is the amount of substance A that is remaining at time t. Beta, so it's not that it has not converted into C yet. Beta minus x is the amount of substance B remaining at time t. So this is the amount that has not converted to substance C also. Okay, so that's chemical reaction. So the number is a constant multiple of the number of interactions between the amount of A and B that is left, is how much C is being created. Okay? So that's our chemistry applications. Mixtures is a very common one as well. Okay, the amount of a mixture at time t is the rate of an element coming in minus the rate of an amount coming out. Okay, A of t is the amount of substance that is in a mixture. D of A is the net rate of substance in a mixture, right? So how much is actually in there at that exact moment. Rn is the concentration in the inflow times the input rate of the mixture. So the input rate, so what is the rate of substance coming in? Okay, R out is the amount of outflow, right? Concentration in the amount that is going out times the output rate. So if you think about this, like in an industrial context, let's say you're making a soda, right? Let's say you're PepsiCo and you're making soda. You have water coming in, you have syrup coming in somewhere else, and then it should be mixing together, right, in this vat, and then you have Pepsi coming out, okay? Maybe you have to mix things in stages, okay? Maybe you have water coming in, and that mixes with the syrup. And then in another vat, that syrup water mixture gets pumped into another vat where you are now adding in other ingredients, right? And so now you have another mixture, and so this can get kind of convoluted. So then now you have a concentration coming in, right? And a concentration coming out. And so your amount at one time is the amount that's coming in minus the amount that's going out. So that's how much is inside. Okay. When we drain a tank, this is also modeled with the differential equation. Okay, so if you think about what it means to empty a tank, you have a tank full of some liquid, water, gasoline, oil, doesn't really matter. Let's say you turn on a hose or a spigot and all of your liquid comes out. Your height is changing over time. The depth of your liquid in your tank is changing over time. The flow rate is changing over time because the more filled your tank is, the more pressure is pushing out the liquid. The lower the tank is, the less pressure to push the liquid out. So there's a lot of things that are changing here, okay? So if we're draining a tank, the volume um, of water, okay, I didn't know if this was in the tank or not, at time t is given by negative A sub h. A sub h is the area of the hole that is used to drain the liquid, the water, okay? This G here is the gravitational constant because the pressure due to gravity should be pushing the fluid out of your tank unless you have a pump connected. And this H here is the height of the water. Okay, so this root 2GH altogether is the speed of the water leaving the tank. So again, A sub H is the area of the hole the water draining out of. Okay, here this is the change in height of the water at any time. So obviously they should be related to each other, right? Because the volume and the height is related. The volume is determined by the height of the water, right? Or the height of the water is, yeah, the volume is determined by the height of the water. So it should make sense that these are fairly similar and that the velocity of the water leaving the tank should be incorporated in both of those, okay? So here we have, basically what we're doing is we're really just dividing by the area of uh, the surface area of the top of the tank, right? So H of T is the height of the water times T. AW is the top surface area of the water. Okay. Doing electrical series circuits, right? Circuits in series. This is also modeled with differential equations. So if you want to be an electrical engineer, you're gonna have to know how to do DEs, okay? So I is the charge, okay? I is sorry, I think this is the current. Current is the charge, the rate of change of the charge at time t. Okay? So IT is the current in a circuit at time t. Q is the charge on the capacitor at time t. So a series circuit should have a resistor, a capacitor, and yeah, that's it. I think there's one more thing that's there as well. Okay, and an inductor. Okay, so the current across the inductor is this I. So the voltage across the conductor is L times the first derivative of I. Okay, if I is the first derivative of Q, that means that the derivative of I is the second derivative of the charge. Okay, so the inductance times the second derivative of the charge on the capacitor. The voltage across the resistor is the current times the resistance. Okay, and the current we know is the first derivative of the charge. So the voltage across the capacitor is 1 over the capacitance times the charge, and the impressed voltage is the total voltage drop across the series circuit. Okay, so LRC series circuit where we have the resistor, the capacitor, and the inductor. And so the impressed voltage, which we call E of T, is L times the first derivative of I plus R times I plus 1 over the capacitance times the charge, right? So we just write this all in chart in terms of Q because that's the derivative that we're looking at in that case. Falling bodies, it's very common in physics. We've talked about this a lot in calculus and algebra. So here, S of t, we've talked about this before several times in this class as well. S of t is the position of a falling object at time t. V of t is the velocity. It is the first derivative of position. Then we have acceleration, which is the derivative of velocity, which means it's the second derivative of position. Okay, so that's the acceleration of a falling object at time t. We know that the force of a falling object or any object is mass times acceleration. Here, this acceleration is the second derivative. Okay, so we have mass times the second derivative of position, which is the same thing as negative mg for something that is falling down, right? We're going, when we say we're falling down, we have negative. Okay, so mass times the gravitational constant close to Earth. And so if I move this around a little bit, I get that acceleration is negative g. Okay, so that's acceleration. Weight, I know, is mass times the gravitational constant. And air resistance, which is related to falling bodies, um, is mass times acceleration. Um, Mass times acceleration is the weight of an object minus a constant multiple of its velocity, right? So the faster something goes, the more air resistance it's going to have. Okay, so here we go. So mass times acceleration is the same as mass times the gravitational constant. And so we use this relationship then to divide both sides by m. Just to be clear, I was like, where does this come from? So we divide both sides by m. And so we have the second derivative. Acceleration is just gravity. That's why we say the acceleration due to gravity. So the acceleration is the gravitational constant. Okay. So negative kV is the viscous damping due to air resistance, right? So mg is the weight of the object, which we know already as well. Okay. So modeling with systems of differential equations. So radioactive decay. Let's say that x of t is the amount of substance x at time t. Then the amount of that substance at time t, the rate of change of the amount of that substance is negative lambda 1 x. So here what we're saying is that x is decaying. Okay, if we say that it decays and turns into a new substance, y, then x is losing atoms. That's why we have a negative constant multiple. Okay, the rate of change of y is gaining atoms from x. Okay, so it's positive here. But if it itself is decaying as well to another substance, then it is losing atoms. Okay, and so this substance z, the amount of z, is increasing, and it's increasing in the amount that it is accepting atoms from the decay of y. Okay, so this one is a nice example of how uh, we could create a system of equations, right? So here we have three equations, and it's all depending on how the previous substance is decaying or not. Okay, notation wise, so this is a physics notation. X decays to y by losing at a rate of negative lambda 1, losing atoms at a rate of negative lambda 1. Y decays to z by losing atoms at a rate of negative lambda 2, okay, at a constant multiple. Then we have what's called the predator-prey model. So this is very, very similar to our population growth, okay, which again, we've seen a similar form of that show up quite a few times here. Okay, so if I have a population of predators, but there is no prey, then that predator population is going to decay at a rate that is a constant multiple of its population size. Because if there's no prey, there's nothing to eat, and you will die off or eat each other. Either way, your population is shrinking. Okay. If I have a prey model, okay, that has no predators, it will just continue to get larger and larger and larger because nothing is eating it. Okay. So we can call these foxes. Let's say I have a population of foxes, and this is rabbits. If there is only foxes and no rabbits, that population of foxes is going to shrink. If I only have rabbits and no foxes, well, that population of rabbits will continue to get larger and larger and larger. Okay. Now, the rate of change of the population of foxes when the two populations interact with each other, I'm going to have a decay because it's a predator um, model, right? So if there was no prey, it would decrease, but the number of interactions between the predators and the prey is going to create growth. So if there's more interactions than there is just the population size, I will have a growing model. However, if I have a small number of interactions compared to the population size, my decay for the population size is going to take over. Okay. Same thing here for the prey model. Okay. My prey model will continue to get larger, but it will be slowed down by the number of interactions between itself and the prey population. I'm sorry, the predator population. So the number of interactions between predator and prey will keep this from growing too much, or if there's a large number of interactions, it will dwarf the size of the growth of the prey population, and its population size will decrease. Okay. This is called a Lotka-Volterra predator-prey model. Two populations are competing for the same resources, then our equations will become this system. Okay, so my prey model, I'm sorry, this is a prey model and this is a prey model. Okay, so it's nothing but growing, but it's going to decline between the number of interactions between the two populations. And if this is the prey model, they're fighting for resources, and so they'll obviously end up killing each other over resources. And so the population is in check by the number of interactions that they have for each other in vying for the same resource. Okay. Next, we have what's called isolated logistics growth. So here, the rate of growth is a population minus mx squared, and this is when the population is basically competing with itself, right? So population is competing against itself for resources, and so it will then lower the amount of its population size. So this is, for example, if you have too many rabbits. If you have too many rabbits and there's not enough resources, the rate of growth is going to slow down. Here, this would be like I have a bunch of rabbits, and then I also have a bunch of deer. They eat the same things, and so they keep each other in check because they're eating up all of their resources that they share together. Okay. So when two isolated logistic populations interact with each other, then we get the following, right? So this population is decreasing because of interactions with itself, and it's decreasing because of interactions with the other population that is competing for the same resource. Same thing here, right? So this is rabbits. The rabbits are competing with themselves, and they're shrinking because they're competing with the deer for the same resources. Same thing here. The deer is growing, the population is growing, but they are competing with themselves, so that's decreasing the population, and they're having interactions with the rabbits, where the rabbits are eating their resources as well, and so that is keeping their population from growing too large as well. Okay, so that's the isolated logistics growth. And so let's do an example. We have two examples. I know it's a long video, but the rest of the videos are a lot shorter for this section. So we have two examples. So the first one is, let's assume that a raindrop is spherical in nature. Okay, starting at some time, which we can call T naught. A raindrop that has a radius of R naught falls from rest inside of a cloud, right? It's gathered enough uh, other water molecules to form a drop and be heavy enough that it falls from the sky, and it begins to evaporate as it falls due to air friction, okay? Friction in the air. So let's assume that a raindrop remains spherical as it evaporates. So the whole time it's falling, let's say it's pretty much a circle, a sphere, okay? Then it makes sense to assume that the rate at which the raindrop evaporates, right, the rate at which it loses mass is related to surface area in some way, right? Because it's the outside that evaporates. The inside of the water drop isn't what evaporates, it's the outside evaporates as it falls, right? So the rate at which it loses its mass has to be proportional to the surface area because that's what's being exposed to um, the elements, to the air, and that's what evaporates out as it falls, right? So we want to show that these assumptions imply that the rate at which the radius decreases is a constant. Okay, so we want to find r of t, right? The function at which the radius decreases. So here, over time, the volume of a sphere is 4 over 3 pi r cubed. The first derivative of volume is surface area, right? I know that the mass is equal to a constant of the velocity, right? I'm saying that the mass dissipates at a rate that's equal to the velocity. And so the volume is a constant multiple of the volume. And so I replace V with the volume function, right? So constant multiple, whatever the mass of water is times the volume of water is equal to the mass of water, right? So mass is some constant multiple of the volume. So now when I differentiate for the change in mass as it falls, I get K, this turns into 4 because the 3's cancel. Pi r squared, because remember my function is r, so I do implicit differentiation, so I get 3 r squared, and then chain rule says I differentiate that inner function, and I got r prime on the outside. This is the surface area. Okay, surface area is pi r squared, 4 pi r squared. So the change in my mass is proportional to a constant multiple of the surface area. Okay. Surface area is pi r 4 pi r squared. So that means that this constant multiple of r prime is the constant of proportionality, right? So I'm gonna say let lambda equal this constant of proportionality. Then I can change this to the change in the mass is some constant multiple of the surface area. Okay. Remember when we want to solve for r of t, right? This r squared that we have in here. So I can move this around and isolate r prime. R prime is lambda over k. I can integrate both sides. Okay. If I integrate the derivative, I get r. So I'm gonna, and remember r is a function of t. So I'm gonna integrate this with respect to t. Remember lambda is considered a constant. K is this constant, right? So then this is just gonna be lambda over k times t, right? Plus a constant through integration. So my radius function is lambda over k times t plus some constant, okay? Remember that my initial radius of the raindrop is r naught, okay? And so what's going to happen then is that if I plug in 0, since it's the initial value, this t will make this part go to 0, and I'll be left with a c equals r naught. So I get to equate the constant from integration is r naught. So my function for the radius of the raindrop then is lambda over k times t plus r naught. And lambda is k r prime, right? So let's do another example. This is the last example. So construct a mathematical model for the number of pounds of salt, which we'll call x1, x2, and x3 at time t in tanks A, B, and C. So this is a nice picture. X1 represents the number of pounds of salt in tank A. X2 represents the number of pounds of salt in tank B, and X3 represents the number of pounds of salt in tank C. Now let's just, before we even build the model, let's kind of look at what's going on. I have pure water coming in at a rate of 4 gallons per minute, and I have a mixture coming out of my tank A at 6 gallons per minute into tank B. I have salt water or salt coming out of B into tank A at 2 gallons per minute. And then same thing with tank C here, right? I have it's leaving tank B at 5 gallons a minute, and it is a mixture is coming in at 1 gallon a minute into B and being mixed as well. And then I have an outflow from C at 4 gallons per minute. Okay. So we want to talk about the number of pounds of salt. So X1 is the amount of salt in A, X2 is the amount of salt in B at time T, and X3 is the amount of salt at C. Um, and we just know that we have pure water coming in. This is some mixture, this is some mixture, this is some mix, this is some mix, and this is some mix, but I don't know the concentration of the mixtures coming into A from B or going into B from A and vice versa, and for the others as well. I don't know the concentration of the mix coming from C into B or the concentration of the mix going from B into C, and I don't know the concentration of the mix coming out of C. And my goal right now is not to solve that. I'm just setting up in a system of equations. Okay, so we're not solving anything. We have not talked about how to solve anything yet. In this an hour and 20 minutes that we've done so far, we've only talked about differential equations, not solving yet. So the rate of change of x1 at time t, so what does that mean? That means it's the number of pounds of salt. So how is the amount of salt changing in tank A as time goes on? Okay, well, I have pure water coming in, I got a mix coming in, and I have a mix coming out. Okay, so, and if we come back, hopefully you have this with you, but let's look how this works, right? For a mixture, I'm looking at the rate in minus the rate out. Okay, and what is the rate in? The rate in is the concentration in my inflow times the rate of input, right? R out is the concentration out times the output rate. So, okay, I know coming in for tank A, for X1, I have 0 salt, okay? So the concentration is 0, and that's coming in at 4 gallons per minute, okay? Coming out, okay, I'm sorry, and also coming in at 2 gallons is some mixture amount. I don't know that amount. That amount is X2 is coming from B, right? So whatever the mixture amount at time T, which is X2, is coming out, okay? And it's coming out per 100, okay? And it's coming out at a rate at 2 gallons. And leaving A at a rate of 6 gallons is the amount in A1, which is X1, divided by 100. So I'm going to subtract the rate that is leaving times the concentration amount, which is some amount divided by 100, some percentage. Okay, because out of this 100 gallons, there is a certain amount of salt. So out of the 100 that's in there, how much of that is salt water? Okay, and so that's why it's over 100. Okay, so 2 over 100 is 1 over 50. 6 over 100 is 3 over 50. And so that's my first equation. And I'm going to do the same thing here. Let's look at what's happening to B. I started with coming in, so let's start with coming in. Coming into B is some unknown amount of X3 out of the 100 gallons that's there, right? And that's coming in at 1 gallon. I also have X1 over 100 coming in at 6. So those are the two things that are being plussed. Okay, so coming in, I have 6 gallons from X1 out of the 100 gallons that's in X1, plus X3 out of 100 at 1 gallon. And then leaving, I have whatever amount's in here already, X2, leaving at 2 gallons, and whatever amount X2 that's in here, leaving at 5 gallons. So minus 2 over 100 of X2, minus 5 over 100 of X2. And I can simplify that as well. 3 over 50, this is just 100. This is 1 over 50, this is 1 over 20. But I can combine like terms, right? So these two X2s I can combine. So it'd be easier just to write this as negative 7 over 100 for this case, right? So 3 over 50, 1 over 100, minus 7 over 100. And I want to do the same thing for tank C. So I did 2 for you. This would be a good time for you to pause, try to do tank C yourself, since I've already done 2 examples, and come back to the video, or I guess press play, see if it matches up. Okay, ready? All right, hopefully you did it. Let's go ahead and see what we have. So coming in, I have this 5 gallons per minute out of X2 over 100. Okay. Leaving, I have some amount of X3 that's leaving at 1 gallon a minute, and that's leaving at 4 gallons a minute. So X3 times 1 over 100, and X3 over 100 times 4 is being subtracted. Okay, combine my like terms, right? Which is just this one. So this is negative 5 over 100. This is 5 over 100. So that's 1 over 20x2 minus 1 over 20x3. And so when I kind of clear this up a little bit, that is what my system looks like. Okay, so that's my system of equations that would model the amount of salt in each of those tanks at, or the rate of change inside of each of those tanks at time t. Okay. All right, I'll see you guys on the next one. You might need to watch this a couple times. There's a lot of information in it. All right, thanks, guys. See you next.